These are your notes for Unit 2, Day 2 of Calculus. If you would like to see the warm-up homework questions or any of the finished or review questions that we covered in class today, just look at the finished notes. So today we're going to talk about derivatives on graphs and what may cause a derivative not to exist on a graph or on a function. We will be able to use the power rule to take the derivative of a constant and power function or polynomial function. We will be able to use and understand the different rules and properties of using the power function with derivatives. And then we're going to talk about horizontal tangent lines for a function. So what are some situations where the derivative wouldn't exist on a graph? So places where a derivative wouldn't exist on a graph would be on that first graph at the point 1, 2. That's called a corner. It's where two lines meet that have different slopes. So notice, if I wanted to take the derivative of this function coming from the right side at x equals 1, the derivative of that coming on the right side of 1, well, the slope of that tangent line would be 0. So if I'm coming on the left-hand side of 1, the derivative would be 0. But if I'm going to come at 1 from the other side, so I'm going to come at 1 from the right side, so if I'm going to try and take 1 from the right side, if I took the derivative of that, well, that's the line 2x, so the slope of that would be 2. So notice that those two derivatives are different. So the slope of the tangent line coming from the left and the slope of the tangent line coming from the right are not equal. So the derivative does not exist. So f prime of x does not exist at x equals 1 because there's a corner on the graph. Those two lines at that point have different slopes, so the derivative doesn't exist. On the second graph, you have a line meeting a curve, and that is what we call a cusp. So when a curve meets a curve or a line meets a curve, we have a cusp. And for the same reason, the derivative won't exist there, because if I look at the derivative coming on the left-hand side, so if I want to approach 1 on the left-hand side and take the derivative, f prime of x would be the slope of that line. And since the line y equals x, the slope of that would be 1. But if I come for the derivative from the right, that would be the function 1 over x. And the slope of that obviously is different. It's negative. So the slope coming from the right-hand side of 1 is not going to be equal to the slope coming from the left-hand side of 1. Since those two slopes are different, or we have a cusp there, the f prime of x does not exist at x equals 1 on this graph because there's a cusp. The slope coming from the left and the slope coming from the right don't exist. You obviously will not have a derivative at any break in the graph. So notice right here, the slope of the graph coming from the left and the slope of the graph coming from the right are different slopes, and there's a break in the graph. So f prime of x is not going to exist at x equals 0 because there's a jump. So derivatives won't exist at jumps, holes, or vertical asymptotes. So the graph has to be continuous for the derivative to exist. So those are some places where the derivative wouldn't exist on a graph and why. So corners, cusps, and any breaks in the graph, the derivative won't exist. So let's look at these. So if we wanted to graph f of x is equal to the absolute value of x plus 2, using transformations, we know we're going to take our parent function and we're going to move it left 2. And so it would be the absolute value of the absolute value graph moved left 2. Where would this graph not have a derivative? Well, f prime of x, its derivative, is not going to exist at the corner. And that corner happens when x is equal to negative 2. So the derivative of this graph is not going to exist at negative 2, but it would exist everywhere else. 1 over x, you should remember its parent function. It looks like this. So where will the derivative of this graph not exist? Well, there's a break in the graph at x equals 0. So f prime of x does not exist at x equals 0 because there's a break in the graph, or there's a vertical asymptote. So the derivative won't exist at breaks in the graph. On the next one, we have a piecewise function. We have x plus 3 as long as x is less than 0. So 3 and then down 1 over 1. So it would be this line. It's an open circle. Or it's the happy parabola that moved 4 down. So 1, 2, 3, 4. And then it crosses over here. And it's going to be a closed circle there because it's or equal to 0. So where wouldn't the derivative exist here? Well, there's a break in the graph at x equals 0. So the derivative won't exist at x equals 0 because there's a jump in the graph, or there's a break in the graph. So it would have two different derivatives coming from the left and from the right at x equals 0. All right, so how do we take the derivatives of some things? Well, if you had a constant, so let's say we just had y equals 3. If we graphed that, that would be 3 up, and it would just be a horizontal line. Well, what's the slope of a horizontal line? The slope of a horizontal line is 0. So if you're going to take the derivative of a constant, the derivative of a constant is always going to be 0. So if f of x equals some sort of number like 3, or pi is a number, or e is a number, or 1/2, or 1.67, if you're going to take the derivative of a constant, if you graph a constant, you're graphing a horizontal line, so its derivative would always be 0 because the slope of a horizontal line is 0. Or using the limit definition of the derivative, f of x plus h, well, it's going to be a constant, right? It's always going to be the same constant. So if I move here, I'm at a height of 3, and if I move a little bit over, I'm still at a height of 3. I'm always at a height of 3 on that graph. So when I do f of x plus h minus f of x, in my example, those are going to be 3 in both cases, and 3 minus 3 is 0. So using the limit definition, you would still get 0. So the power rule, this is going to allow us to not have to use the limit definition of the derivative anymore. So if you're going to use the power rule, you've got 2 steps that you need to take. Step 1 is you multiply by the exponent. So as long as the exponent is just a number, some sort of real number, you multiply by the exponent. And then step 2 is you subtract 1 from the original exponent. So multiply by the exponent first, and then subtract 1 from the original exponent. And that is the power rule. So for instance, if I have f of x equals x cubed plus x squared minus 2x plus 1, the derivative of this would be, the derivative of x to the third is you multiply by the exponent, and then you subtract 1 from the exponent. So this would be 3x squared. So the derivative of x to the third is 3x squared. The derivative of x squared, well, multiply by the exponent and then subtract 1 from the exponent. So this would just be 2x to the first. And then this guy's exponent is a 1, right? So multiply by the exponent and subtract 1 from the exponent. And this would just be minus 2x to the 0. X to the 0 is 1, so this would be minus 2. And then 1 is just a constant. And when I take the derivative of a constant, it's 0. So the derivative of x to the third plus x squared minus 2x is going to be 3x squared plus 2x minus 2. Or if I had f of x equals x to the 3/2 minus x to the 1.5 minus x to the 4th plus 5x to the 7th. Again, same rules apply that we just did before. So the power rule says multiply by the exponent and then subtract 1 from the exponent. So the derivative, the slope of the tangent line, would be 3/2 x. If I subtract 1, I'm subtracting 2 over 2 because that's 1. So I'd get 1/2. Then again, multiply by the exponent. So that would be 1.5x, and then subtract 1 to the 0.5. Multiply by the exponent, subtract 1 from the exponent, so it'd be 4x to the third. Multiply by the exponent, subtract 1 from the exponent, that'd be 35x to the 6th. So the power rule again says multiply by the exponent and then subtract 1 from the exponent, as long as the exponent is a real number. So the constant multiple rule, we covered that. If there is a constant in front of the function, so if f of x is equal to 3x to the 6th, you can take that 3 and multiply it afterwards, or you can multiply it as part of the problem. So I'm going to multiply by the exponent and then subtract 1 from the exponent, and the derivative of this would be 18x to the 5th. So if there's a constant in front, you take the constant and you multiply it by the exponent and then subtract 1 from the derivative, subtract 1 from the exponent. So if I have f of x equals the square root of x plus 1 over x to the 5th plus 3 over x squared. And one like this, we're going to have to rewrite it so we can see the exponents first. So f of x is equal to x to the 1/2 plus x to the negative 5th. So if the variable is in the denominator, bring it up. And this would be plus 3x to the negative 2. So if I want to take the derivative, multiply by the exponent. So this would be 1/2 x and then subtract 1 from the exponent to the negative 1/2. then multiply by the exponent, negative 5x. If I subtract 1 from negative 5, I get negative 6. And then 3x to the negative 2 would be negative 6x. If I subtract 1 from negative 2, I get negative 3. So my derivative would be 1/2 x to the negative 1/2 minus 5x to the negative 6 minus 6x to the negative third. So let's go ahead and just do some basic ones. So what is the derivative of f of x equals x squared minus 2? Well, the derivative of x squared would be 2x, and the derivative of negative 2, since it's a constant, is 0. So the derivative would just be 2x. The derivative of 2x squared minus 4 would be 4x. The derivative of negative 4 is 0, so it'll just be 4x. The derivative of 2x to the 10th would be 20x to the 19th, and the derivative of negative 4x squared would be negative 8x. So we get 20x to the 19th minus 8x as the full derivative. So sum and differences, just like when we did our limit properties, if you're taking the derivative of the sum of two things, you can take the derivative of it one at a time. So if we had f of x equals 5x squared plus 6x minus 2, that's a sum of three different things. So you can take the derivative of them one at a time. So the derivative of 5x squared is 10x. The derivative of 6x is 6, and the derivative of negative 2 is 0. So we took the derivative of those one at a time. So the derivative overall will just be 10x plus 6. The same thing works if we're subtracting, so it's the same idea for sums and differences. All right, so more examples. So let's say we have f of x equals x to the 4th divided by 4 plus x minus 2. Sometimes it's helpful to rewrite it as 1/4 x to the 4th instead of x to the 4th divided by 4. That might be easier for you guys to see what the derivative would be. So this would be multiply by the exponent. 1/4 times 4 is 1, and then subtract 1 from the exponent. So that would be x to the 3rd. The derivative of x is 1. The derivative of negative 2 is 0. So the derivative overall would be x to the 3rd plus 1. On the next one, let's rewrite it. So this would be 5x to the 3rd minus 5x to the negative 3rd. So if the x is in the denominator, pull it up and give it a negative exponent. So the derivative of this would be 15x squared plus 15x, and then be careful, negative 3, when you subtract 1 from that, you get negative 4. So it'll be 15x squared plus 15 times x to the negative 4th. Next one, again, rewrite it. So this would be x minus 1x to the negative 1. So 1 over x is the same as x to the negative 1. And if I took the derivative of this, the derivative of x is just 1. And then this would be plus 1x to the negative 2. So that would be the derivative of the bottom one. All right. You guys, go ahead and see if you guys can rewrite ones that you would need to rewrite and try and take the derivative of each of these. You can pause the video and try. All right, so the derivative of the first one, you multiply by the exponent. So 4 times 5 halves would be 20 halves, which is 10. So this would be 10x. And then 5 halves minus 1 would be 5 halves minus 2 over 2. So that'd be 3 halves. So that'd be 10x to the 3 halves. On the next one, I'm going to rewrite it as 1/2 x squared minus 3x. And so if I take the derivative of that, 1/2 times 2 is 1. So this would be x to the 1st. And then the derivative of negative 3x is just negative 3. X to the 1,000th, if I took the derivative of that, multiply by the exponent, 1,000, and then x to the 999. Subtract 1 from the exponent. On the next one, I'm going to rewrite this as the square root of 3 times the square root of x, which is the same thing as square root 3 x to the 1/2. So when it's a square root, it's the same thing as x to the 1/2. And so if I took the derivative of this, you multiply by the exponent, so it'd be square root 3 times 1/2 would be square root 3 over 2. And then subtract 1 from the exponent, and that'd be x to the negative 1/2. The next one I'm going to rewrite. This would be 8x to the negative 1/2, and then minus 3x. So if I took the derivative of that, 8 times negative 1/2 would be negative 4, and then subtract 1 from negative 1/2, and you get negative 3 halves, and then minus 3 for the derivative of negative 3x. All right, so same thing. See if you guys can pause the video and try and take the derivative of each of these. All right, I'm going to rewrite it as negative 3s to the negative 2, and then minus 4s to the negative 4. And if I took the derivative of this, I would get positive 6s to the negative 3, and then plus 16s to the negative 5. On the next one, I'm going to rewrite it. So that would be square root 2 times s to the 1/3 plus square root 2 times s to the 1/5. So the cube root is to the 1/3 power, fifth root is to the 1/5 power. So if I took the derivative of this, it would be square root 2 over 3 s to the negative 2/3 power, plus square root 2 over 5 s to the negative 4/5 power. Again, I'm just subtracting 1 from the exponent. All right, so the equation of the tangent line now using the power rule. So if I wanted to find the equation to the tangent line of f of x equals x squared minus 4 at the point x equals 3. So we've got our happy parabola moved 4 down, and I want to find the derivative of this at 3. So the slope of the tangent line at x equals 3. So first we need to find the slope of the tangent line. The slope of the tangent line is going to be the derivative. And so the derivative of x squared minus 4 is just 2x. And they wanted me to find it when x is 3. So it's going to be f prime at 3. So 2 times 3 is 6. So the slope of my tangent line is going to be 6. So at x equals 3, the slope of my tangent line is 3. Well, in order to write the equation for a tangent line, you need both slope and a point. Well, I know I need x to be 3, so I need to know what's the y value there. To find the y value, you plug into the original function. So we're going to plug back into the original function to find the y value that matches up when x is equal to 3. So f at 3 is going to be 3 squared minus 4, which is 5. So I have the point 3, 5, and the slope of my tangent line is 6. So if I wrote the equation for my tangent line, I would get y minus 5 equals 6 times x minus 3. And that would be the equation for my tangent line. So that's the equation of the tangent line at x equals 3. All right, so let's go ahead and do that top one together. So y equals 5 halves x squared plus 1/2, and we want to write the equation to the tangent line at the point 1, 3. So first, let's find the derivative. So y prime equals multiply by the exponent, subtract 1 from the exponent. We would get 5x. The derivative of 1/2 is 0. And if I want to find the derivative, this is when x equals 1 and y equals 3. So plug in 1 for x. This would be 5 times 1. So it would be 5. So that's the slope of my tangent line is 5. And I need it to pass through the point 1, 3. So y minus 3 equals 5 times x minus 1. All right, you guys go ahead and try the one below it, and then you guys can check your work against the finished notes from class today. All right, let's go ahead and again, the top one, you guys can pause the video, try it, and then check your work against the finished notes from class today. And let's work on that bottom one together. So I'm going to rewrite this. Y is going to equal 3x to the 1/2 minus x. So if I took the derivative of this, I would get 3 halves x to the negative 1/2, then minus 1. In order to plug in x equals 4, I'm going to rewrite this. This is the same thing as 3 halves times x to the negative 1/2 means x, the square root of x is in the denominator. So it'll be 3 over 2 square root x, and then minus 1. I want to know what that is when x is 4. So this is going to be 3 over 2 times the square root of 4 minus 1. Well, this is going to be 3 over 2 times 2, so it would be 3/4 minus 1. And 3/4 minus 1 is going to be negative 1/4. So the slope of my tangent line is negative 1/4. I need to know what the y value is so I can have my point. So if I plug in 4 into the original equation, I would get 3 times the square root of 4 minus 4. So that'd be 3 times 2 minus 4, so my y value is going to be 2. So I have the point 4, 2. And the slope of my tangent line is negative 1/4. So the equation of my tangent line would be y minus 2 equals negative 1/4 times x minus 4. All right, horizontal tangent lines. Horizontal tangent lines, well, horizontal lines are when the slope is 0. So where do horizontal tangent lines exist on a graph? Horizontal tangent lines are going to exist at the peaks and the valleys. So horizontal tangent lines are going to exist at the local mins and maxes on a graph. So again, your slope of the tangent line, so you need the derivative to equal 0. So you need the slope of the tangent line to equal 0 for it to be a horizontal tangent line. So we need to know when is the derivative equal to 0. So when will this tangent line have a horizontal, when will the tangent line be horizontal? So for this to be true, you need the derivative to equal 0. So our first step is we need to find the derivative. So the derivative of this, y prime, is going to equal negative 6x. We need this to equal 0. So we need the derivative to equal 0 for there to be a horizontal tangent line. Well, that is when x is 0. So if they just want to know where, then you would write when x is 0. If they want to know the point, then you would take this and plug it back into the original function. So y equals negative 3 times 0 squared plus 4. So you would have a horizontal tangent line at the point 0, 4. So if you were to graph that graph, it's a sad parabola moved 4 up, and it's narrower than normal. So notice at the point 0, 4, you would have a horizontal tangent line to that graph. Let's look at the bottom one. So we have y equals 2/3 x to the third minus 7/2 x squared plus 6x. And we want to know where would this have a horizontal tangent line. So it wants to know when would the derivative of this be equal to 0. So let's find the derivative first. So if I multiplied by the exponent and subtracted 1 from the exponent, I would get 2x squared minus 7x plus 6. And we want to know when is that equal to 0. So we would factor it. Can you multiply to 12 and add to negative 7? Yep, it would be negative 3x and minus 4x plus 6. We want to know what that's 0. So factor by grouping, pull out an, that's not an x cubed, that's an x squared. So pull out an x, and you would get 2x minus 3. Pull out a negative 4, and you get 2x minus 3. So you get x minus 4 times 2x minus 3 equals 0. So either x is 4 or x is 3/2. So those are the two locations where you would have a horizontal tangent line on that graph. So if you were to graph it, that's where the peak and the valley would exist on the graph. So higher order derivatives. You don't just have to take the first derivative. You can take something called the second derivative, the third derivative, the fourth derivative, the fifth derivative. So in physics, if your original function is displacement, if you take the first derivative, you're getting the velocity. If you take the second derivative, you're getting something called acceleration. If you take the third derivative, you're getting the jerk, and so on and so forth. So find each derivative. So this right here is the notation for the second derivative. So remember, dy over dx is the first derivative. d2y over dx2 is the second derivative. d3y over dy3 is the third derivative, and so on and so forth. Or you can do y prime, you can do y double prime, y triple prime. That's another way of saying these. So if you wanted to find the derivative, you just do it the normal way. So the derivative of negative x squared would be negative 2x, and then it wants you to find the derivative. So y double prime would just be negative 2. You take the derivative of the derivative. On the next one, it wants the third derivative. Well, the first derivative is negative 4. The derivative of negative 4 is 0. So the second derivative is 0, and the third derivative is 0. The next one wants us to find the fourth derivative. Well, let's find the first derivative first. The first derivative would be negative 20x to the third. The second derivative would be negative 60x squared. The third derivative would be negative 120x. So the fourth derivative, or you can do, instead of putting all those little prime signs, you can just do y, and then in parentheses 4, would be negative 120. So you guys go ahead and find these two, and you can check your work against the finished notes from class today. So pause the video and try those two. All right, so displacement, velocity, and acceleration. So if displacement is your original graph, f of x, if you were to take the derivative of displacement, you get velocity. So the slope of the displacement graph is how fast you're going, right? So if I looked at the slope of this line right here, I went 4 up and 5 over, so 4/5 meters per second is how fast I was going right there. So the velocity graph, if I were to graph it, would be at a constant rate. So it would be a horizontal line of 4/5 that entire time. So if I were to graph the velocity graph, that first piece between 0 and 5 would be at a constant velocity of 4/5. So the derivative of displacement is velocity. The derivative of velocity, or the second derivative, is acceleration. So if you looked at the slope of a velocity graph, so right here, notice the slope from there to there, I went down 4 and over 1, so negative 4 over 1. And we have meters per second per second. That's an acceleration unit. So the derivative of velocity, So v prime of t, the derivative of velocity, is acceleration. If you took the acceleration's derivative, you get something called jerk. So if you're thinking on a roller coaster, it's like, and you feel that jerk going back and forth, that is the third derivative. That's called jerk. So, gentlemen, your homework is on Canvas in your modules. So go ahead and